In this video, we're going to look at another example of moments and centroids. The goal here is to find the centroid of a region by applying horizontal strips and integrating with respect to y. So the rows of x and y are now reversed. Consider a lamina with constant density rho whose boundary is formed by continuous function x equals g of y equals c, y equals d, and x equals 0, the y-axis. We begin by looking at this horizontal strip and ask ourselves what is the centroid of this horizontal strip. Well, the x-coordinate is simply going to be 1/2 the x value, so 1/2 g of yi, and the y-coordinate is simply going to be yi bar. That's the distance to the x-axis is the y-coordinate. So we apply the same Riemann sum arguments as before, and we obtain the centroid integral formulas, but now they're in terms of y rather than x. All right, so let's develop these formulas. Mass is equal to density times area. So density times integral from y equals c to y equals d, g of y, dy. The moment with respect to the y-axis is the integral from c to d. And what is the average distance to the y-axis? That's going to be 1/2 the x value. Well, x is g of y, so that's 1/2 g of y times the mass of this horizontal strip is rho times g of y dy. Then the integral adds up all of these moments. So this part, 1/2 g of y, is the average distance of this horizontal strip to the y-axis. This is distance. And this part is the mass of this horizontal strip. Mass. Mass times distance gives us the moment. The integral adds it all up. And we find the total moment with respect to the y-axis. All right, so now let's develop moment with respect to the x-axis. The moment with respect to the x-axis is going to be the distance to the x-axis is simply y. And we're integrating with respect to y, so we'll just leave it as y. Times the mass of this horizontal strip, which is rho g of y dy. This part here, y, this is distance. And this part is mass of this horizontal strip, mass. Mass times distance gives us the moment, and the integral adds up all the moments, then we'll get the total moment with respect to the x-axis. So x bar is equal to moment with respect to the y-axis divided by the mass, and the moment with respect to the y-axis is rho times integral from c to d, and we have g of y times g of y, so we get g of y squared, so 1/2 g of y all squared, integrate with respect to y, divided by the mass, which is rho times integral from c to d, g of y dy. Now rho cancels out. There we go. So you can see how the centroid doesn't depend on the density because it's a constant density that cancels out in the numerator and denominator. Now let's develop y bar. Y bar is equal to the moment with respect to the x-axis divided by the mass. And the moment with respect to the x-axis is going to be rho times integral from c to d, y times g of y dy. That's the moment with respect to the x-axis divided by the mass, which is rho times integral from c to d, g of y dy. And again, of course, rho cancels out, and the centroid is independent of the density. All right, so we have now developed the formula for the centroid x bar and y bar, and we've done integration with respect to y. So let's look at an example. Where this formula can become applicable. All right, so what we have is here we have find the centroid of the region in the first quadrant bounded by the graphs of x equals 2y cubed minus y to the 4 and the y-axis with density rho is equal to 3. You can see how it would be, if you try to integrate with respect to x, it would be impossible because you have to solve for y in terms of x, and that's not even possible. Or it would be extremely difficult, and the integration would be all the more difficult. So integration with respect to y is necessary, and that's why we develop these formulas. So let's now talk a little bit about the sketch of this function. So here we have x is equal to 2y cubed. Let me change color. X is equal to 2y cubed minus y to the 4. All right, let's factor out y cubed times 2 minus y, and let's find the y-intercept. So y cubed equals 0, That gives us third root both sides. You get y equals 0. And plug y equals 0, so we're making x equals 0 and solving for y. So y is 0, x equals 0. That's just the origin. Now let's make 2 minus y equals 0. And we get y equals 2, x equals 0. These are these points here, 0, 0, and 0, 2. Now, what about this part here? You can see there's a vertical tangent here. How do we find vertical tangents? Well, we know how to find horizontal tangent. When we had a horizontal tangent, we just made the derivative 0, dy dx equals 0. But that's not the case here. We're looking for a vertical tangent. So we're going to make dx dy equal to 0. If we make dx dy equals 0, we'll find the y value where we have that vertical tangent. So dx dy, differentiate x with respect to y, we get 6y squared minus 4y cubed equal to 0. Let's factor out 2y squared times 3 minus 2y equal to 0. 2y squared equals 0. We get y equals 0. Let me write that better. Y equals 0. And 3 minus 2y equal to 0. Solving for y, we get y equals 3/2. So that gives us an idea. You can see y equals 3/2 is roughly about here. It gives us an idea of where that vertical tangent is, and it aids us in drawing this. And there's another one, of course, at y equals 0, vertical tangent. All right, so now let's do the computations and apply the centroid formulas. Mass is equal to density times integral from c to d, g of y, dy. The density is 3 times integral from 0 to 2, 2y cubed minus y to the 4 dy. This is equal to 3 times, what is the integral of 2y cubed? That's 2y to the 4 over 4. What's the integral of y to the 4? That's y to the 5 divided by 5, applying the reverse of the power rule. Evaluate from 0 to 2, and now apply fundamental theorem of calculus. Mass is equal to 3 times. Put the upper limit in, 2 to the 4th is 16 times 2 is 32 over 4. That's 8. Minus 2 to the 5, that's 32 over 5. Put a lower limit in, that's 0 minus 0. Now let's add these fractions. 3 times 5 is a common denominator. 1 goes into 5 5 times. 5 times 8 is 40. Minus 5 goes into 5 1 time, that's 32. 5 times 8, 3 times 8 is 24. 24 over 5. So the mass of this lamina, this plate, is 24 over 5 is equal to 4.8. Now we need to find a moment with respect to the y-axis and, of course, the moment with respect to the x-axis so we can find the centroid. The moment with respect to the y-axis is rho times integral from c to d, 1/2 times g of y squared. That's the formula we developed earlier. So the moment with respect to the y-axis, the density is 3. Integrate from y value of 0 to y value of 2, 1/2, and g of y is 2y cubed minus y to the 4th, all squared dy. 1/2 is a constant, passes through the integral, so we get 3 over 2. Integral from 0 to 2. Now let's fold this out. 2y cubed times 2y cubed gives us 4y to the 6. Multiply the two terms, multiply by 2, we get minus 4y to the 7. And minus y to the 4th squared, we get plus y to the 8 dy. All right, so what we have is moment with respect to the y-axis is 3 over 2. Integrate from 0 to 2, 4y to the 6. We simplify the integrand, make it easier to integrate. Minus 4y to the 7. Now we can integrate term by term and reverse the power rule and solve. So a moment with respect to the y-axis is 3 over 2 times. What is the antiderivative of 4y to the 6? That's 4y to the 7 divided by 7 minus, what is the antiderivative of 4y to the 7? That's going to give us minus 4y to the 8 divided by 8. And integrate y to the 8, that's reversing the power rule, add 1 to the exponent, y to the 9, divide by the same. Now we're going to apply fundamental theorem of calculus, put the upper limit in and the lower limit, and subtract 3/2 times. We get 4 times 2 to the 7, divide by 7, minus 4 times 2 to the 8 divided by 8 plus 2 to the 9 divided by 9. I'm putting 0, it's just going to give us 0. Now let's look at the moment with respect to the x-axis. The moment with respect to the x-axis is density times integral from y equals c to y equals d, y, g of y, dy. The density is 3 in this case. Integrate from y equals 0 to y equals 2, y times g of y, which is 2y cubed, minus y to the 4th, dy. So the moment with respect to the x-axis is equal to 3 times, let's simplify the integrand, then we'll integrate term by term. Y times 2y cubed gives us 2y to the 4. Y times y to the 4th, that gives us minus y to the 5. Put this all in brackets, integrate with respect to y. Now let's integrate term by term. What is the integral of 2y to the 4th? That's going to give us 2y to the 5 divided by 5 minus an integral of y to the 5, reverse the power rule, y to the 6 divided by 6. Evaluate from 0 to 2, apply fundamental theorem of calculus. The moment with respect to the x-axis is 3 times. Now put the upper limit in, we get 2 to the 5 is going to be 32 times 2, that's I guess 64. I'll just write it as 2 to the 6 here, divided by 5, minus 2 to the 6 divided by 6, minus 0. All right, if you simplify all of this, add up all the fractions, we'll obtain mass is equal to 24 divided by 5. And the moment with respect to the y-axis, if we simplify all the fractions, add them up, we get 64 divided by 21. And the moment with respect to the x-axis is going to be 32 divided by 5. All right, so what we have is mass is equal to 24 divided by 5. Moment with respect to the y-axis is 64 divided by 21. Moment with respect to the x-axis is equal to 32 divided by 5. X bar is equal to moment with respect to the y-axis divided by the mass. So moment with respect to y-axis is 64 divided by 21 divided by the mass, 24 divided by 5. Flip the denominator, we get 64 divided by 21 times 5 over 24. Simplifying, we get 320 divided by 504. If we decimalize this, put this into a calculator, we get approximately 0.64. Now y bar, the y coordinate of center of mass. Moment with respect to the x-axis divided by the mass. The moment with respect to the x-axis is 32 over 5. And of course the mass is 24 over 5. 5 cancels, we get 32 divided by 24. If we decimalize this, we get approximately 1.33. So we have found the centroid x bar, y bar to be equal to 320 divided by 504, 32 divided by 24, which is approximately 0.64. The x-coordinate is 0.64, and the y-coordinate of center of mass is 1.33. Now, always ask yourself, does this make sense? Let's go back to the diagram and see if it makes sense. So this is kind of like a partial check on your solution. So we found the x-coordinate of center of mass to be 0.64. Well, that kind of makes sense. That's roughly about here, 0.64. And the y-coordinate is 1.33. It's roughly about there. So, for example, if you get an x-coordinate of center of mass to be, for example, 5, then you know it doesn't work. Or if the y-coordinate of center of mass is outside the region, say the y-coordinate of center of mass came out to be 3 or 4, then you know it's not possible. So that's like a check on your solution, a partial check on the solution. Does it make intuitive sense? All right, thanks.